welcome back. Today we will have lecture 8-2 on discrete time systems analysis, stability, and settling time. What you will see here is the characteristics are the same as they were for the continuous time systems, but the methods that we use to evaluate them are different. The objectives of today's lecture are students should be able to analyze the transfer function of a discrete time system to determine if the system is asymptotically stable. Students should be able to analyze transfer function of a discrete time system and determine the overall settling time. In discrete time, the behavior of the unit impulse response as n approaches infinity determines the asymptotic stability. If the magnitude of h of n goes to infinity as n goes to infinity, the system is unstable. This means that at least one pole of the system is outside the unit circle, or poles of multiplicity greater than 1 are on the unit circle. At least one pole has a magnitude larger than 1, or poles of multiplicity greater than 1 have a magnitude of 1, i.e. the magnitude of z equal e to the at is greater than 1. If h of n goes to 0 as n goes to infinity, the system is stable. This means that all poles of the system are inside the unit circle, or all poles have a magnitude less than 1, or the magnitude of z equals the magnitude of e to the at is less than 1. If the magnitude of h of n is bounded or less than or equal to some number m as n goes to infinity, we say that the system is marginally stable. This means that there are some poles on the unit circle with no more than a multiplicity of 1, and the other poles are inside the unit circle. Figure 1 shows the unit circle with the regions of asymptotic stability. Note that the sampling rate t can affect the transient response of a system, such as the type and stability. The settling time for a system is found by examining each of the poles, similar to continuous time analysis. The estimated 2% settling time is Ts is equal to negative 4t divided by the natural log of the magnitude of the pole, where t is the sampling period. The overall settling time is the one that takes the longest to die off. The dominant pole for a system is the pole that yields the overall settling time for the system. The dominant pole will be the one that is furthest away from the origin because it takes the longest to die off, while also considering that the system must still be stable in order to settle. Unlike analog control systems, in digital control systems, sampling rate actually does affect the transient response as well as the stability, as stated before. So here we have the unit circle, where if all the poles are inside the unit circle, it's stable. If any pole is outside the unit circle, it's unstable. And as long as you have poles of multiplicity 1 on the unit circle and the rest inside, you have marginally stable, but at no point can you have a repeated pole on the unit circle. In class activity 1, determine if the system described by the following transfer function is stable, unstable, or marginally stable, and justify your answers. So we have z over z plus 0.25 plus j 0.47 times z plus 0.25 minus j 0.47. So if I make a plot on the real and the imaginary axis, where here is my unit circle, what we have here is we have a 0 at the origin, and we have our two poles here and here at negative 0.25, 0.47, negative 0.47. Since all of these are inside the unit circle, we have a stable system. In class activity 2, determine if the system described by the following transfer function is stable, unstable, or marginally stable, and justify your answer. Z over z minus 4 times z plus 0.5 plus j 0.5 times z plus 0.5 minus j 0.5. So once again, we draw the z plane, where this is our real axis, this is our imaginary axis, and here we have the unit circle. And we're going to put the 0 at the origin. We're going to put a pole out here at 4. And we'll have poles at negative 0.5 plus or minus j 0.5. So this is negative 0.5 plus or minus j 0.5. And what you see here is that all of the poles And all the poles are not inside the unit circle because we have this one out here at x equals 4, at z equals 4. So we have an unstable system. Now let's try in-class activity 3. So once again, we make the z-plane. Here's the real axis. Here's the imaginary axis. Here's the unit circle. It's 1 over z times z plus j squared. So this one does not have a 0, but it does have a pole at the origin, and it has a repeated pole at negative j. Remember, this is negative j. And because this has a multiplicity greater than 1 on the unit circle, we would say that this is unstable. Finally, in-class activity 4. Determine if the system below is stable, unstable, or marginally stable, and justify your answer. Z over z plus 0.707 plus j 0.707 times z minus 0.866 plus j 0.5. So first, I will draw the z-plane again. Here's the real axis, the imaginary axis, and here's the unit circle. 1, 1, negative 1, negative 1. First, we put our 0 at the origin here. And then we're going to have one pole at negative 0.707 minus j 0.707. So here's negative 0.707 minus 0.707. So that puts one pole here on the unit circle. And over here, we're going to have a pole at 0.866 minus j 0.5, which is going to put a pole here on the unit circle. So we have two poles on the unit circle, but it's not a multiplicity greater than 1. So here we say that this system is marginally stable. In-class activity 5. The following discrete time transfer function has a sampling interval of t equal to 0.3. What is the estimated 2% settling time? So first, z over z minus 2 has a 0 at the origin, and it has a pole at 0.2. So the formula is the settling time equals negative 4 times the sampling period over the natural log of the magnitude of the pole. So this is going to be negative 4 times 0.3 over the natural log of 0.2. So the settling time is 745.6 milliseconds. For the following discrete time transfer function, there is a sampling interval of t equal to 0.1. What is the estimated 2% settling time? Once again, we have a 0 at the origin and a pole at 0.67. So the settling time is negative 4 times t times over the natural log of the magnitude of the pole. So that's negative 4 times 0.1 over the natural log of 0.67. So the settling time is 998.81 milliseconds. In class activity 7, the following discrete time system transfer function has a sampling interval of t equal to 0.3 seconds. What is the estimated settling time? So now we have a transfer function that actually has 3 poles. So 2 of them are actually complex conjugates, so they'll have the same magnitude. So we have to find 2 different sets of settling times to see which one is dominant. So we're going to have t equals 0.1 here, and t equals negative 0.2 plus or minus j 0.1 here. So here the magnitude of z is simply 0.1, but here the magnitude of z is 0.223 607. So over here the settling time is negative 4 times 0.3 over the natural log of 0.1, which is 521.153 milliseconds. Over here the settling time is negative 4 times 0.3 over the natural log of 0.223607, which yields a settling time of 801.14 milliseconds. So remember, the dominant pole is the one that takes the longest to settle. So this means that because 801 milliseconds is greater than 521, both of these are the two dominant poles, and the overall system settling time is 801.14 milliseconds. And recall that the way we could find this out quickly is by looking at the unit circle. The dominant poles are going to be the two that are the furthest away from the origin. So 0.2 plus or minus j 0.1 are here and here, while 0.1 is right here, so it was closer to the origin, so that was not the dominant pole. And now let's do the final activity in today's lecture. The following discrete time transfer function has a sampling interval of t equal 1 second. What is the estimated 2% settling time? H of z is equal to z over z plus 0.25 plus j 0.47 times z plus 0.25 minus j 0.47 times z minus 0.5 minus j 0.5 times z minus 0.5 plus j 0.5. The good news is we have two pairs of complex conjugates here. So I actually only have to do the calculation for the settling time twice. Over here, we will have z equal negative 0.25 plus or minus j 0.47. And over here, z is equal to 0.5 plus or minus j 0.5. So over here, the magnitude of z is 0.532353. Over here, the magnitude is 0.707. So thinking about what we talked about earlier, we already know that the one furthest away from the origin is this one. So these are going to be my dominant poles, but we will go through and do the math to confirm. So over here, the settling time is negative 4 over the natural log of 0.532353. So the settling time is 6.345 seconds. Over here, the settling time is negative 4 over the natural log of 0.707. So the settling time is 11.537 seconds. So as we stated earlier, negative 0.5 plus or minus j 0.5 does take longer to settle. So the dominant poles are 0.5 plus or minus j 0.5. And the overall system settling time is also 11.537 seconds. And this concludes today's lecture on discrete time systems analysis, settling time, and stability. Have a great day.